Students, in this lecture 2, I will start with the power in the different AC circuits. So first coming to the pure resistive circuit. As we learned in the previous lecture that the voltage V is equal to V naught sin omega t and I is equal to I naught sin omega t in the resistive circuit. So the power P can be written as the product of voltage and current. So we will get P is equal to V naught sin omega t I naught sin omega t. Solving this, we will get P is equal to V naught I naught sin square omega t. Now, to calculate the average power, first we have to integrate this power over the time period t and then divided by total time period t. So we will get it something like here, and converting the sin square omega t term into 1 minus cos 2 omega t, and then again solving further and integrating, we will get the next term here, where the integration of cos 2 omega t over the time period gives 0, and so the average power value will be equal to V naught by root 2 and I naught by root 2, which can be written as P average is equal to Vrms and Irms, where Vrms is equal to V naught by root 2 and Irms is equal to I naught by root 2. RMS stands for the root mean square. Now coming to the pure capacitive circuit. So as we know that in capacitive circuit V is equal to V naught sin omega t and I is equal to I naught cos omega t. So the power will be given by P is equal to V naught I naught sin omega t into cos omega t, which further can be written as V naught by root 2 I naught by root 2 sin 2 omega t, which will be turned as Vrms Irms sin 2 omega t. Again, to calculate the average power, we have to integrate the power over the time period t and divide by the total time period. Then again here, the integration of the sin 2 omega t over the time will be 0, so the average power will be 0. In the pure inductive circuit, we have V is equal to V naught sin omega t and current I is equal to minus I naught cos omega t. Calculation of the power will again give the similar values as in the capacitive circuit, but with a negative sign. So integrating this power over the time period capital T will again give us 0 value, and so the average power in the inductor is also 0. So coming to the LCR circuit. So here, as we know that the voltage applied is V equal to V naught sin omega t, but here we are not sure what will be the current, so we will assume that I is equal to Im sin omega t minus phi, where Im is the current amplitude and phi is the phase by which the current lags the driving voltage. So here we have to find the value of Im and phi. To do so, first we will differentiate the current equation and we will get di by dt is equal to omega Im cos omega t minus phi. Also, integrating the current equation, with respect to t, we will get the I dt is equal to minus Im by omega cos omega t minus phi. Integration of I over time t will give the charge q, and so we have the two terms di by dt and q. Now in the figure we can see that there are four voltages which are VR, VL, VC and VT. So VT is the applied field and VR is the voltage across resistor, VL across inductor and VC is across capacitor. The voltage VT applied to the circuit will be equal to all the three voltages VR, VL and VC. As we know that VR is equal to IR and VL is equal to VL is equal to L di by dt and Vc is equal to Q by C. So the sum of all the three voltages will be equal to the applied voltage. Here we have written uh, applied voltage equal to epsilon m sin omega t, where epsilon m is the voltage amplitude. Now putting the value of I di by dt and q in this equation, we will get this equation given in the yellow highlight area. Now using the trigonometry, sin omega t minus phi is equal to sin omega t cos phi minus cos omega t sin phi, and similarly expanding cos omega t minus phi, and then collecting the sin omega t and cos omega t terms separately in the equation in the highlighted area, we will get the following two terms for cos omega t and sin omega t. For cos omega t, we will have the term omega L minus 1 upon omega c cos phi minus r sin phi is equal to 0. The sin omega t term will contain Im omega L minus 1 upon omega c sin phi plus Im r cos phi is equal to epsilon m. Now solving those equations for the phi and Im will give that tan phi is equal to omega L minus 1 upon omega c divided by r, which can be written as xl minus xc by r, where xl and xc are the inductive reactance and capacitive reactance, and r is the resistance of the resistor, and Im will be equal to epsilon m by z, where z is the total impedance of the circuit, which is given by z is equal to under root r square plus xl minus xc square. So after exercising the AC circuits, we get the maximum current, that is the peak current value Im is equal to epsilon m, or we can also write it or say as Em by Z, and tan phi is equal to XL minus XC upon R, which is the phase angle. XL is equal to omega L, which is inductive reactance. XC is equal to 1 upon omega C, which is capacitive reactance, and Z, which is total impedance, is equal to under root R square plus XL minus XC square. From this phase diagram, we can also understand the reactance and the relation between them. So if R is the resistance of the resistor used in the AC circuit and XL and XC are the inductive reactance and capacitive reactance respectively, then there will be a phase difference between them, and which can be given as here. So you can see that the tan phi is equal to XL minus XC upon R. So the Z is the resultant of R and XL minus XC, which is represented in the figure. So the tan phi is equal to XL minus XC upon R, and cos phi is equal to R by Z. The cos phi is also called the power factor in AC circuit. So in summary, we can say that we have learned about the different resistance reactance of the AC circuit and the phase angle between the current and the voltage. So these are the summary which you can learn from here. In the next lecture, we will start from the resonance in the LCR circuit and the power in the LCR circuit.